So I've titled this Control Equals Prediction plus Engineering. I think this is the grammar that I use to think about these sorts of questions. I have an amazing postdoctoral associate in my lab who's here, who I sat down and he said, I didn't know you worked on causal inference, right? And I said, well, looks like we have a lot to know about each other, but I think we're going to use the grammar of kind of prediction, which is largely what we use in the evolutionary and bioengineering paradigms, which is the ones in which I operate today. Before doing anything else, really, I want to acknowledge the organizers of this meeting, everybody who supported this. This is one of the coolest and most interesting gatherings I've been at in my several years at Yale. I always say that this institution needs more kind of renegade nerd gatherings. There's not enough, and this is absolutely qualifies as one, so I appreciate everyone who supported and all of you, of course, for attending, all of the individuals in my research program, all the individuals who've supported this work in various ways through the years, and of course, a large library of mentors, mentees, former mentees who are now mentors, people who now support me in various ways. They've influenced this work in various ways through the years. And my newest family, the Santa Fe Institute, which has really been important for integrating this dimension of my research program and further my identity for asking questions that are related to what we're discussing here at this workshop today. So I want to make sure they are acknowledged. The reason why I titled the talk to my title came from some popular writing. I was actually writing the article on the top where I actually introduced this really just conceptual framework for thinking about how we're thinking about controlling evolutionary biology in various settings, largely in the construction of biomolecules. And I came up with this framework, control equals prediction plus engineering. And it's really just like I said, it's a conceptual anchor for how to think about how the types of information we need to be able to control a complex biological system, right? And I kind of use this as an anchor for the rest of this talk, but mostly we're going to be focusing on the prediction component of this, since that's kind of the one related, not the same as, but related to causality. How do I enter these problems? Well, I think my basic science program, I've been described as a lot of different things. I give a talk at many different sorts of scientific audiences, so depending on who I'm around is the way I'm described. But a computational biologist mostly, and we use a range of methods where we use disease to ask fundamental questions kind of about the way nature works. And I think on the flip side, we use kind of theory in various paradigms to potentially improve how we think about disease and epidemics. But I think there's another component of my research program which is going to be very, very active here today, and I think it is active really in all areas of my program. And that's kind of the intersection between data and culture. I think this is something that began as something that I was doing for, just because, but this has actually become a real technical paradigm for my work. And I think it dances very, intimately with some of the other dimensions of my work. So you'll be introduced to this as well. But I think really there's been a combination between these identities recently, right? Like I said, and I think really where I land is that I focus on how interactions shape constraints in biological systems, okay? So whether we're talking about engineered systems or we're talking about artificial systems or informational systems, really you can define, we can define all of them by what are the guardrails around them, what are the things that are actually shaping how those systems are constructed. In my sense, the way things evolve, these interactions shape by a molecular evolution, right? They constrain how epidemics manifest, and they constrain science in the world in which it is embedded. So this is really how I can frame. I call myself an interaction nerd. I like when I put things together and I get something surprising, and I kind of use biological systems to be able to ask those sorts of questions, okay? Now, when we think about what a constraint is, I think this manifests in all the talks that we heard. We heard this outstanding, just this morning, we've heard about different constraints in the way they shape the systems of interest, be they cosmological, be they anthropological, be they cellular, be they biophysical. We can think about a lot of ways. And so this is like one dimension of constraint where I mostly live. I study proteins, and I study kind of protein folding. And here you have an enzyme, right, dihydrofolate reductase, who basically catalyzes a reaction at different rates and different temperatures, right? So in this situation, right, temperature is a context which is kind of constraining what this enzyme can do. And in my lab, we identify kind of the way this constrains the way it evolves. It sets the expectations for the way this sort of protein evolves. We can think about constraint this way. If many of you work on the kind of ecosystem ecology scale, or if you think about climate change, you think about species distribution, or any kind of really, even this is in many ways geopolitical. All right, you can think about forces operating on this level. Some of us kind of live in this level here, me less so, right? This is, any New Yorkers in the audience, this is the Queensbridge, okay, good. This is the Queensbridge houses. So this is the largest public housing complex in the United States now, and it's home to all my heroes from growing up. And I think one of the great questions is, what is it about neighborhoods like this that give birth to so many people gifted with words in terms of hip hop artists? Right, and this is something that was very, very important to me. We think about this in a lot of contexts. So what is it about these sets of constraints and contexts that kind of created that opportunity for that sort of linguistic advancement? But then, of course, this one, right, these constraints are tied together. And it's not different than when we heard about scales, right? I think there's resonance between these things. There's a relationship between some of those constraints we talked about, for example, like that constraint. That relates to that constraint. But this constraint, of course, in this context, of course, did not grow out of the ground. This one came out because of constraints like this, historical constraints, okay? Like they were active decisions made by Homo sapiens about who could live where and who could be, how you treat certain people and what have you. So the point is that all areas of my research program and all areas of all the things we're discussing here in this, right, with relation to causation and inference, they're being shaped by various forces, okay? And so what I'm going to argue is that, right, the success, if you will, or the effectiveness of causal inference and, or in my case, prediction or control is really going to be grounded by, right, our understanding of the way these sorts of constraints influence our systems of interest, our understanding of them, our ability to parameterize them, right? And that really is, right, that's kind of the framework that I approach these sorts of questions with. And so we'll meet various components of these in various actors. Now, I'm not nearly as smart enough to study this and this well enough. There's people who have studied this for centuries infinitely better than I ever could. But I have found the attempt to do so, right, to attempt to be the idiot in the room, and right, when we're reading about that sort of thing, to be refreshing, and it has added to the dimensions of my work in many ways. So, like I said, we're going to get through a lot, right? So we're doing okay? All right. So control, prediction, it's engineering, right? So again, like I said, right, these sorts of constraints are actually shaping our ability to predict, and really they're shaping the engineering, and they shape our ability to control systems, complex systems of interest, right? And today we're going to talk about two different systems, right? Genetics and evolution. We got this outstanding talk today that did a lot of the work for us, right? So I can skip a lot of that, so thank you for that, Professor. And epidemics, these are both biological, quote unquote, systems, right? And they have many things in common. So what we're going to do is we're going to kind of talk about a little bit of a history of how we think about prediction and causation in these realms. Very, very little history, right? We're going to talk about the modern times, like what are the contemporary issues and challenges for thinking about these. And then I'm going to hopefully end with a little bit of like positivity with regards to new ways for thinking about how we can think about prediction more carefully. And both of them, I'll introduce a new theorem in the process, a funny theorem in the process. So history and genetics and evolution, we can kind of think about a lot of ways, a lot of really smart. David, I don't know how you feel about this, but this is kind of one way of one way of capturing like the era we've been in. I know I think the modern age probably needs it. We're kind of like, in some ways, we're in the age of genomics, but in some ways we're in a different era. But what we're going to focus on now is the modern evolutionary synthesis. We got a really, really great primer for that earlier. And I think importantly, right, this era is the one that really transformed kind of biology into a quantitative field. Of course, as you know, everybody who does empirical science of any kind has been profoundly influenced by Fisher's work, right? But really, it was about the fusion of these Darwinian and Mendelian schools and kind of formulated evolution as a quantitative science capable of describing and explaining the process of evolution. And so pretty much right away when we got these quantitative tools to be able to, potentially treat a biological system like a physical one, pretty much right away, right, people went right came up with like these new fundamental ways to describe how populations work. We were able to describe and understand what had happened for millennia with regards to artificial selection and agriculture and domestication. So it was really one of the most powerful sets of understandings that we've ever come up with, I think, and I will defend that. But of course, with that came false prediction as well, and it came some errors as well, right? And of course, that we can cast that in the eugenic movement. The notion that we can take these kind of discrete principles and apply them to human population, right? So when we think about this, and I think this is kind of the challenge when we're thinking about how to understand systems well enough to understand cause and effect, or causal inference, or understand prediction, right? There's breakthroughs, and then there's questions about what we do with those tools, and then there's kind of technical misgivings that oftentimes lead to certain problems. And we see the signature for both the beauty and the problems of this paradigm today, right? So
I mean, it's a great time to be in this profession. I think we're doing all kind of important things with genomic technology. You might have saw the approval of the first CRISPR kind of truly CRISPR-driven therapy for sickle cell anemia that was just recently approved. So I mean, it's really one of the most amazing times to ever think about, living systems in this way, right? And so we can think about things like genomic prediction, and we can think about genetic engineering in ways we've never been able to. We can wire organisms mutation by mutation in order to kind of get to phenotypes of interest. We can, right? But of course, with that comes things like this, okay? And I don't know, we had a conversation over dinner, so I want to make sure I put this in. Because this actually, I don't know how many, maybe raise hands, anybody seen this film? All right. I got a big raise back there, right? Well, good, I don't have to feel bad. This is pretty nerdy, what you're gonna see. So I actually wrote a paper about this that made the cover of Genetics, right? And the idea here is we kind of use the film to have a conversation about this exactly, right? The whole thing is, how are our predictive tools doing? We use the film to have a contemporary conversation about where we are with this sort of technology, right? And we actually review things like embryo selection, right? What are the statistics about it? How good are we? How good are we not? And they actually got a lot of things quite right in the film 25 years ago, right? So again, right, cultural relics and cultural things end up being this important kind of substrate for us to be able to think about the contemporary technical issues when we're thinking about causation and prediction. Okay, but of course there's many other conflicts, okay, right, many others, okay, so even things that I participated in, like the precision medicine paradigm, the notion that we can treat every single individual here according to their peculiar biology, I mean, it's just riddled with a lot of kind of technical misgivings. We've already seen genetic discrimination happen. Obviously, some of you are a part of these conversations about genetically modified technology. So these are some of the areas where, despite all these breakthroughs and excitement, we have a lot of contemporary questions, right, about what it is that we're doing here, okay? And of course, the rise of extremism and fascism and race science, which of course is another older, right, this goes back to eugenics, but of course has been reanimated, right? So what we talked about here was kind of this history of how genetics kind of has thought about this sort of problem, and some contemporary things that we should be very, very excited about, and some other things that we should be very, very cautious about. And I think the same thing goes for how we think about the epidemics. And of course, long history of epidemics. I'm going to capture it in 2 slides, but kind of modern public health as we understand it. Some of you know this story about kind of the water pump, and it was cholera, and it was the identification of the source being a water supply is the birth of, by many opinions, of public health as we know it today. And of course, mathematical epidemiology, which is one of my paradigms, again, can be traced to many people. There's a long history going back, but I think one of the modern iterations that some of us, I learned they actually teach in physics here, which I was very, very happy to hear in intro physics here. They actually teach dynamical systems to the biology majors, and it's basically this notion of how you can understand and mathematize a population undergoing some kind of infectious process. And this goes back to 1927, okay? So again, long history doing that, a lot of successes, lots of failures, but we can kind of animate that now and what those contentions and challenges are with regards to, because the point is when you model something, presumably you understand what its character is such that you can potentially predict it. Like that's the point. You want to be able to understand who you need to vaccinate and where you need to intervene and what have you. And I think this, of course, has been animated here, in case you haven't been paying attention. And of course, the roles of modeling and what we were predicting and how was really one of the central conflicts of, right, the pandemic era, and remains so. And I think mathematical modeling was kind of on trial, if you will, in this sort of way. And so it had to kind of, we had to kind of reflect on whether, what are we modeling, how are we modeling it, are we using the right tools, what are the assumptions that we're making, right? This ended up being something very, very important that was essential. Now, in the face of this, I did some mathematical modeling of this, but most of my work, again, we're going to return why I think this sort of meeting and why I'm so grateful, Priya, for this sort of gathering is the multidisciplinarity is not just nominal. It really, you really actually learn from it. You learn what the important questions are from engaging. Because I did a little bit of this, but I did much more of this. Much more public engagement. I became kind of a misinformation warrior during the pandemic, right? So I did some mathematics, right? And what I learned about the pandemic and the way we engage it is that there's several challenges that I think that are common to both genetics and epidemiology, right? So when you think about causation and prediction, right? I think the ethical is the technical in some ways, right? So I think these are separate paradigms with different grammars, right? But part of the conversation, a lot of the things that we think are ethical are actually, right, rooted in technical challenges that we have, right, in being able to properly predict the shape of an epidemic, or being able to properly predict what the phenotypic effects are of a mutation, or what's in the genome, or the relationship between genotype and phenotype, right? And you know, it's rooted in, right, we might be really swell people, but our ideas might be bad, right? I mean, in particular in the genomics context, right? You might have good intentions, and I'm not here to judge anybody's intentions with regards to being able to predict whether or not baby A or B will get into Yale or not. You might have good intentions, right? But the ideas that you're using to be able to kind of, you know, influence that prediction, of course, might be bad. And of course, this applies very firmly to a lot of the conversation with regards to ethical AI, right? But I was talking to someone, I think you, about time scale yesterday. The time scale consequences and effect on accountability, sometimes the negative consequences are too downstream for the people who are, right? So if I mispredict the shape of an epidemic like 2 years from now, and I come up with a harmful policy, right? Is that time scale for which that's wrong and causes harm, does that match up with me being held accountable for my bad decision making up front, right? So this is one of the problems. There's not a lot of cost for me getting things wrong when I'm making these incorrect predictions, and that sure as heck goes in the genomic context when you don't see the consequences for your actions for generations. So I think there's that challenge that we have to deal with. But more than that, are we thinking about complex biological systems correctly, right? And this is where we'll go next. I have some kind of frameworks for how to think about this. And so, you know, understanding the role of constraining context and shaping, it can really help our predictions. I think there are frameworks and understandings and concepts in both genetics and epidemics that can actually help us kind of wade through this. One of the things I try to fight through when I think about these sorts of complex biological systems with a lot of different processes of information is to not be nihilistic, right? The point is not that everything is hopelessly complicated and so we shouldn't bother. Maybe some of you think that, but like, right, that's not where I live. I think it's more about understanding what the specific roles of those contexts. So we'll talk about these two things. What are some constraints that govern complex biological systems? In genetics, we have gene by environment interactions. You might have heard that one. That one is reasonably popular. And that is the notion that you can't really tell what the consequences of a gene or a mutation are doing. You need to know something about the environment you're in, right? I think the second one is what we'll talk briefly about today, gene by gene interactions. It's a concept called epistasis, and it's a little bit odd, so we'll spend a second there. With epidemics, host-parasite interactions, I think anybody that's ever been sick knows what that means. But host-host interactions is the way that people are interacting, influence the dynamics of disease, you bet. But then there's other social forces that can interact with how hosts, right, or interact with other hosts, and by extension are interacting with parasites. And these are the sorts of interactions, like I said, that are actually shaping these complex biological systems, and by extension, influence, right, causal chains, and influence predictive, the possibility of prediction, okay? So we'll start with genetics, okay? Now we'll start with this concept called epistasis. It's been called the dark matter of biology for the physicists, right? Or the dark matter of genetics. Now, what is it exactly? This is a great colloquial definition from a mentor and friend, Dan Weinreich, a theoretical population geneticist. The surprise at the phenotype when mutations are combined given the constituent mutation's individual effects. I know what mutation A does on it by itself. I know what mutation B does by itself. I put them together and I get a whoa, the surprise. And that's like legitimately what it is. I have this fun graduate student analogy. I have two extraordinarily talented graduate students in my lab. When they combine, so these are their, is there a pointer? It's on here, right? Oh, yes. Right, so both of them are positive, right? This is kind of the y-axis is just how good they are. So they're extraordinary, both of them. You put them together experimentally, right? And you get this additive effect, right? As in you just add them together. When they're coding together, you get this extraordinary kind of non-linear positive interaction, which means they code together beautifully. But when I ask them to write a paper together, they actually like have a negative interaction, and they get less work done together than either of them would have been done individually, right? And that's really what we're talking about with mutations. I mean, I think they have these different sorts of interaction effects between mutations. Now, why is this important? I mean, this completely rewires how we think about the importance of the individual mutation or gene in dictating phenotype. if all your phenotypes depend on interactions between genes, and we're talking about 20,000 and 50,000 and 100,000 genes, then the problem, I mean, astronomical is too small to think about how quickly this, right, combinatorial explosion creates a mess here, right? Unless we have some tools, I believe this for this crowd. Yeah, we have the point of this is just we have a whole host of statistical tools to be able to resolve out higher order interactions. I think I look around the room and look, you all have them. In fact, we've borrowed this from theoretical computer science. This is the Walsh-Hadamard transform, which is, comes from, noise stuff in engineering and computer science. But we now apply it to how we can resolve out and come up with the algebra, basic algebra for how we can resolve out how epistatic interactions are occurring between genes, right? Right, but again, this nihilism question, okay? Is this a nihilistic understanding? If everything has to interact with everything else, isn't that kind of a hopeless feeling, right? But thankfully, there's some new concepts with regards to epistasis that I think give us rhyme and reason, and that's called global epistasis. This basically says that there are fundamental rules governing how those interactions between those graduate students happen, such that I can potentially predict them. So even though they're nonlinear and they feel surprising when it happens, there's actually an underlying physics of kind of interacting information. And this is pioneered by Alvaro Sanchez, my close colleague. And we've done this work, we've done a bunch of work on this recently. So, right, they also often follow systemic patterns that enable predictability, and and this kind of changes our relationship with a concept that would otherwise be nihilistic, right? We now have this understanding that, wow, we can actually do something about this to understand this phenomenon. And now this is being animated all across kind of genetics and genomics to add rhyme and reason to phenomena that seem to undermine predictability. Okay. Sorry. All right. Right. So again, global epistasis suggests that fundamental rules, there's fundamental rules for these sorts of interactions such that they can be predicted, and we'll kind of know not to make them write papers together. Right. Now, shifting to the epidemic context, right? We talked about host-parasite interactions, right? We're going to talk about the sorts of constraints that influence them, and what are some different ways we can think about prediction and causation in this system, all right? So one of the things that I've studied is the kind of mathematical and computational models of hepatitis C virus. We call this the silent epidemic for a bunch of reasons, right, having to do with the people it affects, it's people who inject drugs, and how, like the natural history of the disease kind of can make it challenging to understand, but nonetheless, it's extremely important, right? And so what we did is we actually we created a mathematical model that if you think about a disease that's spread by people who are sharing drug paraphernalia, it has features in common with a vector-borne disease, right? And so this is exactly what we did mathematically. We basically, published here in 2019. But something very important happened in this work, right? When we were doing this work, I found myself in Reddit forums of people who were users, right? Because I'm trying to understand some things about the way that the disease is transmitted. And in that, I got very, very guilty because I said, here I am trying to mathematize something with all of this social import. This is something that's really, really affecting people, okay? Now, right, part of the reason why this became important mathematically is I began to think and learn more about the way social forces are actually crafting the thing that I'm trying to mathematize, okay? So that ends up being a serious and important dimension for how we're thinking about modeling and predicting the shape of these epidemics. I can't possibly understand anything about disease if I'm not engaged with the forces that are actually influencing the hosts, okay? So again, right, a reason why to engage these different disciplines. And of course, there's other social forces, and I began to work on this. I've worked on this, right, how kind of policy regarding prison influences the dynamics of a pandemic in multiple dimensions, right? So what we're seeing here is, right, in the context of epidemiology was, right, I'm interested, I have a complex system composed of all of these elements, and I want to know, how to predict it. We can think about causation in this system, and we're identifying all of these constraints that influence what those predictions will be. And this paper here is really one of my favorite. It's, admittedly by two good friends of mine. But I think it's one of the most important papers I think I've read in epidemiology in quite some time. And they introduced this notion from physics called permutation entropy, right, which kind of has this other life, but they apply it to the case of epidemics. And this is what they say. Here's the model that we did for hepatitis C virus. And so we don't, for those, one of the things, innovations we did is we modeled needles as their own population. And so we can actually think about what happens when you take needles out of a population, for example, with a safe injection sites or with needle exchange, these sorts of public health interventions that allow you to actually directly deal with the problem of needles. So that was one of the kind of conceptual innovations to this mathematical model. What this paper says is that if you want to predict the shaping of an epidemic, okay, the problem is the parameters themselves change as the epidemic is happening, right? And so you are hopeless in trying to predict an epidemic past a few days. And of course, it'll depend on disease, it'll depend on things, right? But it introduced kind of this idea that it really is a fruitless venture to try to come up with a universal, long-term predictive algorithm. It doesn't work that way because the parameters are changing too fast, right? And I think this is the innovation here. And I think this had a big effect on me because this is the sort of thing. It's not that we can't predict, it's that perhaps we should be changing what our goals are for prediction. It's not that we can't understand causal chains, it's how far apart they are when we're talking about the actors and their consequences in epidemiological systems, okay? And so this is what we mean about prediction, right? Now, we talked about this in various frameworks. We talked about this in genetic systems, the sorts of things that both undermine prediction in genetics, but potentially, right, there's utility here. The global epistasis framework potentially allows us to predict. In the context of epidemics, we can talk about something similar. I think the permutation entropy framework helps us. And what I'll leave is with something very, very, right, with a concept. This is my son, and he's a toddler, okay? And anybody that's ever been around a toddler knows predicting what your child is going to be is a very, very important, like that's kind of part of what being a parent is, right? I have a prediction that he's going to live with me at 30, but by the way he acts now, but you never know. Now, as useful as it would be for me to be able to, it's very important, as useful as it would be able to be for me to predict that he's going to be quarterback for the University of Michigan, it's actually much more useful for me to be able to predict when he'll be able to nap tomorrow, right? So the notion that a long-term prediction is better or holistic is better is just not true, right? I think we should learn to be, right, somewhat satisfied or, in fact, goal shift to tuning our expectations, in particular with regards to time scale for our predictions. And that is, right, if we have very, 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 very strong predictive ability for tomorrow, that's actually actionable. That's not actually any less rigorous technically. And I think it completely changes how we think about a lot of these complex biological systems. Yeah, anyway. Great. That's all.
Thanks, Brandon. Thanks for very interesting to point out that that time scale over which predictions are made is sort of fundamentally relevant because in public policy frameworks and contexts, you need to make decisions. And it's fine to say for astronomical systems, right, I can predict 2 galaxies that will merge in 10 to the 7 years or whatever, right? So, yeah, thanks for bringing that into focus. Questions?
Great. Thanks so much for your very rich talk. I just wanted to maybe think together a bit more just about constraints and the role they play. Because it seems to me there's kind of, so some people just think of constraints as like additional causes or stable causes you haven't measured. I guess my suspicion has always been that they're much richer. That's not just some like causal variable that you could have intervened on that you didn't include, but can be something. I mean, we have historical constraints or long patterns or sometimes, these timescale dependent behaviors. It really feels more like a fundamental characterization of the system, and there's no translatability. So I was just actually I'm really trying just to open up a conversation about if you have a thought about how to model constraints. Is it just,
Yeah, no, thank you for that. I mean, I think, take a problem like antibiotic resistance evolution, which is something that I think about, right? It's a complex problem. It's an evolutionary problem. It's a molecular problem. It's a protein problem. We study that problem from the angstrom scale. But when you think about kind of the likelihood of evolving something like that, this is where multidisciplinarity is essential. It's not just like fun to talk to people. Half the problem is people's willingness to take drugs on a certain schedule, right? So if you are not that is a constraint that the system, that is actually dictating the pace and the direction of evolution of antimicrobial resistance. So I think I like your definition in the sense of it's all, it's all of the things, and we don't need to know all of them, right? But we need to know the ones that meaningfully influence the dynamics that we are trying to predict and or establish causal chains between. So that's how I think about constraints, and I think the challenge is the silos. Right, we're not trained to think very, very broadly about some of these other dimensions, or we're unwilling to do so, or we don't have people who bring them together in this sort of way. And I think this is why a lot of my work, I've gained tremendously from being able to open up that dimensionality.
Thank you. Shyam?
The problem of prediction in sociobiological systems like epidemics, where there's a feedback loop, prediction itself can cause conditions that will make that prediction untrue, which is very different from pure physical systems and so on. And
100%. Yeah. More than anything, I mean, I think that's true. You see that.
what do we do on, how do we deal with the problem of prediction in social systems?
Yeah, no, I mean, again, I'm the not negative one about these sorts of things in a lot of rooms. Yeah, I mean, mathematical modeling has got a lot of things right. There are a lot of conditions that it actually was able to properly characterize or understand. And I think that is because we had a proper understanding of what the constraints were in that system. So I think if we have an understanding of kind of what the way that people are interacting, and we understand what the constraints are, I think we have a lot of successful iterations of where we've predicted the trajectory of epidemics quite well. So it's not a hopeless task. It is just one where our expectations need to be modified by our understanding of what the constraints are. That's what I would say.
I mean, and I guess it also behooves like continual updating of predictions,
Yes.
right? So it's
Yes.
not like you made a prediction, it's out there.
Yes.
It's a very live process.
Yes.
Eduardo and then Janan.
Thank you, Brandon. I think I'm going to follow up on the conversation we had yesterday overnight. What makes me think a lot, we keep talking about understanding, we keep talking about knowledge, and when I hear colleagues like you and other colleagues who are much more at the boundaries between applied and very translational science, more and more I'm asking myself, who needs to understand? Who needs to know? Because at one level, I feel like we're at a time where we feel like every citizen has to understand how the vaccine works. Are we going to expect to understand how that bridge that I'm going to cross with a car was built? And so I don't think, I think it's creating a lot of social issues, confusion, problems that have really, affect us all. What are your thoughts on is it thinkable that at so many levels, we don't need everyone to understand? It used to be that I would go to the doctor. You did a pregnancy test. You were not asking, how does the urine work with the strip, etc. You assumed you were pregnant, you moved on. And my worries is that, again, in the talking and being some of us pushed to do more and more outreach, and it's getting all very confusing, and people don't know if they're listening to the peer-reviewed oral version of the paper, if they're listening to the scientist, if they're listening to the scientist, educator / citizen. And I really think that there's some positive aspects to the science being siloed. Everyone feels like they need to know and understand, but not everyone has spent 30 years looking at disease transmission.
Yeah, my opinion is, that's a tough one, right? So things are easier when they're siloed and less democratic in that way, right? When there's less, less input from the public,
Well, at least there's a partition between experts and non-experts.
Yeah, when there's a partition between,
clear,
it's easier. We don't have to answer. I guess my job would be easier if I did not feel like I was compelled to communicate it with my grandmother, right? I would just be able to do the science and talk to you. Unfortunately, that's not how I think. That's not where I think my job is. So I don't agree with that, right? I'm actually deeply pro-democratization of science. I want a future where citizens can actually participate in the scientific process. Now, we're a long way from that. That's utopian perhaps.
No, but also highly problematic, right? Because the sources of getting information now,
Right.
and disinformation and misinformation.
But it's problematic now, even within. It's not like we're doing the job well
Right.
as professional scientists. There's misinformation now within professional science. There's gatekeeping within professional science. There's discrimination within professional science. So I think we need to stop looking at ourselves as a paragon for the way that it works, because it doesn't. It works for us.
But
We're doing fine, but I know a lot of people that aren't.
But the way we think of democracy is not having 300 million people voting 24/7 for every single thing that we do. I mean, that's a referendum. It's not a democracy. And then democracy, I used to defer to my doctor who, in some way, I decided he knows. And my dad told me, you ride the bike this way. I didn't decide to go figure it out myself.
Right.
So there has to be some trust
No,
in
I
those
understand,
people.
but my mother has faced discrimination in the medical community often. And if she did not have me there to ask questions of the experts growing up, she would have had a shorter life, frankly. So that's my point. Yeah, it's easier for me to trust the person with the expertise, and that would have made it quicker, and that would have made it easier, and the physician might have felt better about not having to answer a question from a poor black woman. But the right thing to do was for him to answer the questions that she had about what the decision was being made.
Yeah, I mean,
Of course, it's easier the other way, but it's wrong.
Yeah, no, absolutely. And I think part of the issue really is with the openness comes certain kinds of risks, right?
Yeah.
So when we are not yet done finishing our understanding or analysis,
Yes.
and we are sort of in process,
Yes.
that is now open to the public, right? And I think that creates a lot of possibilities. So I think we have to think very hard about how to democratize and how to open up the processes of science as inference, really, right? I mean, because that's what the public really wants to know. How are you arriving at this conclusion when you're giving me a directive? I think Samantha put it really nicely, right? That even if you give the right information, decision-making is really complex, right?
Yeah.
People may not actually use they may just go for the simplest version of the information that you can provide, which may not be fully accurate, right?
I agree with both of you
Yeah.
intensely, and then also have work on discrimination in medicine, which is will lead to new fears for everyone. Basically, if you tell your doctor things that they disagree with, they'll like you less. So great.
I've seen it happen.
Great news. But for me, it's more about this expectation that like we should all be informed about everything, which is just humanly impossible, right? You can't read up about every single decision you want to make, and that shouldn't be an expectation we create for people.
But I feel like every time we talk about that, we turn the dial up to everybody doesn't need to understand everything in the universe, and that's not. There's a lot of levels between where we are now and that.
Everything, yes,
Like,
yes.
what I learned in the vaccine era is people just wanted to know how it worked.
Yeah.
Once they learned how it worked, they went and took the vaccine. I get calls to this day. I get emails to this day. Something I said on a podcast got their whole family vaccinated. Because I just took the time to explain. Like, it's not everybody wants to have access to everything ever, and we got this, we're going to be fighting for seats because everybody in the community who thinks they understand what causation means. That's not the reality. And in fact, the reality that we've created has created the war on science.
Right.
The silos has actually created, right, the substrate for society to distrust science. So we need to completely break that and prove that.
Right.
Anyway.
And the question is whether the inferential process should be in full public view, how much of it should be in public view, or whether it should be in public view or not, is a big sort of question to debate. Janelle?
Too quickly, I want
Yeah.
to go back to the point that Sean made, which is it's a very different setting where knowledge itself is endogenous. And if knowledge is changed, what knowledge you have, and the way the knowledge feeds into the system is affecting the system. That means that you can't stabilize the system as an objective knowledge, because everything that you know about is going to change the system. Very different setting from traditional science, where we take ourselves out of the system, and deeply important in exactly the realms that you're talking about.
Thank you for that.
Yeah, Tim?
This is just a short comment. In terms of, I understand this discussion, and there's certainly a big problem with communicating science and motivating people to behave the right way. And to say a lot of the problem arises from within, but let's not ignore that the fossil fuel industry undertook a $1 billion campaign to misinform people, that, you know, the tobacco industry undertook $1 billion campaigns to misinform people, and with the intentional effect to undermine faith in science. So I don't know that we should blame I mean, we have our bits of blame, but yeah, you know.
My question is, what do we do in the face of that? That's my question. So is the answer that because the fossil fuel industry flooded the industry of billions and misinformed the public, and I work on topics related to that, that I'm not culpable to do anything about it? Is that the answer?
No.
No.
But,
No, you do something about it. You actually, we should be the ones going to war with these people. This is what happened with eugenics.
right.
I mean, the other option is unconscious.
I mean, but I think Tim is absolutely right that there have been established playbooks. So at some level, we have the advantage post hoc of knowing how these misinformation and disinformation campaigns can work and have worked, and in what ways they are successful. And I think I really like the various threads that have come up, right? It is a conundrum, right? If we are able to show and reveal as expert scientists or people working with data sets and inferring from data sets, whatever be those data sets, even if that process is fully demystified, it's unclear because you have these other outside forces that are sort of banging at the door. So the question is, given that is the reality, is talking about how we relate effects and causes and how we arrive at decisions and how individuals then incorporate that information and make decisions. It's a very complex space, right? But I think we all share responsibility to do something about it. Okay, 1, 2, and 3. I
Yes.
want to go to coffee, so I want to be attentive to
Yes,
that.
thank you. This is fascinating conversation. And at the expense of opening a can of worms.
Better be a small can.
Very,
It's better be
very
a
small can,
now,
very
right?
small
Okay.
can called AI. My question is, will it, if and when we have trustworthy, reliable, robust products and services, AI products and services, will that help democratize science? For example, your mother would have, instead of asked you and took you with her to the doctors, she could have had her phone and asked, an AI specialized product. What do I do with the doctor? What do I tell the doctor?
Look, I'll just end here by saying I find myself oddly pro-technology in a lot of these conversations relative to my friends, right? When you've seen discrimination happen in person, you don't. I'm just not sure I'm not sure that the algorithmization of it is worse.
Right, but I mean, the question is,
I'm not convinced.
Right, no, but Brandon, but if the algorithm
Of
has been arrived at with biased
Of course.
training sets,
Totally right.
it's going to be no better.
No, totally right. I just don't have faith in people like that.
Right. Right. So,
Great
had a
question,
question
isn't
there.
I
Quick
can bring
question.
it up at the coffee hour.
Okay, great.
Yeah.
Okay.
Thank you all.
Okay, maybe we just wrap it up and head out to coffee. But